Dr. Gold in the lab, Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while them haters count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing out the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
All right, what's up, everybody? So I need Discord working here. Good. All right. I need this to be correct. There we go. Good. Okay, cool. Nerosky's here. Nice. All right, let's start the event off. There we go. Let me bring Nerosky to the stage. And then here, let me cast this. Good evening, Nerosky. Or good morning for you, probably.
Good morning, yeah, for me, but good evening for everybody else.
Yes, evening, morning. It's all, time is a continuum. And we're just figuring it out. All right, let's get this going. Oh, River's here, too. What's up, River? River, you ready to learn some awesome math? River's very self-motivated in learning, I know, right?
Yeah.
Cool stuff. River says yes. Hell yeah. Okay, awesome. Nice, nice, nice. Okay, let's see. Do I got this set up? Yep. Okay, cool. All right. Welcome, everyone, to the Gilded Method featuring Nerosky. This is a fun new series of streams. Nerosky actually came to me at the end of last year and said, hey, wouldn't it be cool if we had a stream just dedicated to like elegant math and like competition stuff? And he volunteered to maybe teach us some awesome, cool math tricks that I know sometimes scare kids just looking for homework help. But it's okay, because I was like, oh, well, this is perfect. Let's maybe make a fun little separate series. Because we do have a lot of people on our Discord who are very interested in learning beyond what's taught in your classroom, which is sometimes absolutely nothing.
No.
So, great. We're going to do that today for the next... I scheduled out 2 hours. You don't have to go the full 2 hours if you don't want to, Nerosky. But I'm cool.
No, it's okay.
It's good? Okay, cool.
Yeah.
So, yeah. How about, Nerosky, you want to give like a little briefer introduction about who you are and then... give us a first topic to go through and we'll start learning some stuff.
Yeah, sure. So for everybody who hasn't actually tuned in to the streams yet, I'm a student in high school, currently studying math at an Olympiad level, and I came across these streams a few months back in 2025. I actually came off of YouTube. And
YouTube.
actually,
it's good we started streaming on YouTube.
A problem that caught my attention was actually proposed on stream in a night where I was doing like my own math quizzes, and I noticed it was it was odd for math to pop up on my feed anyway. And it was difficult as well. It was actually a competition question. It was from International Olympiad, I believe, a few years ago.
Mm-hmm.
And yeah, I provided my own proof for it, and I had to join the Discord to attach it somewhere, right?
Yeah, we had to see the solution.
Yeah, and ever since then, I kept tuning in whenever I could.
And you've been an amazing help with anytime I get stuck with these nightmare questions, dude. You're always there, like it's like my little guardian angel for math, and I'm just like, oh, nice. This is how you actually do it. So
yeah,
I
it's fun
appreciate
because I've seen you like adopt a few new methods of writing like your own solutions because of it.
I have, yeah. I've started learning. I learned too, guys. You know, it's not just all teaching you guys. I learned some shit as well with you guys. Cool, nice. All right. So here, let me clear off the board of things. Delete all of these pages. Wait, like clear all the pages. And then, what do we want to work on first here? Or here, I'm gonna give you a lot of freedom into like just like deciding what we go through. Did we want to do this? Did this make sense? This one, the trace one?
I believe it. I did finish it last night, right after the stream closed.
Mm-hmm.
I had a few moments to think about it, and it wasn't that difficult, right? So I did attach the photo for it in the chat.
Okay, let's go check it.
Yeah, we can go look through it right now. Really quickly.
Yeah, let's go look at. Let's learn some stuff. All right, let's see. That was in. Where's my homework help stream? Oh, there it is. Okay. And then it was. Oh, here we go for tomorrow. Got it. Here it is. Okay, good. Cool. All right, sweet. Nice. Okay. So we started with. We did get to this, right? I remember getting. What was it? Here.
Yeah. Yeah,
this I agree
with. That's a very important part of this because we're gonna base our entire solution off of that.
Okay. Everything's based off of getting to this point, which, to remind the watchers or the viewers, I think all we did was we just expanded these two things out of the first statement because we say like this is true if and only if this is true. So it's kind of a good idea to try to, I guess, restructure the first statement into something like just an equation.
Yeah, and since my thinking here is, as I said before, if you look at the statement, like what it's asking you to prove, it is a symmetric statement. So if you take it from one end or the other, it should be symmetrical. So it doesn't matter if it is if and only if, right? That would mean equivalence. So you'd have to go both ways.
Yeah,
but
so in proof language, they write that like this. Is this kind of what you're saying? Like, we could have started with this too, I guess, right? If this is true, this has to be true as well. Okay.
So this is called necessary and sufficient, right? So going from left to right is necessary. And it is sufficient if you go from right to left.
Okay, do we have to prove both? Are we going to have to prove left to right and right to left?
The way to avoid doing this is either going with equivalence all the way through, so going with equivalent statements. This is rare, but it still happens sometimes, yeah. That avoids it because every statement is basically if and only if, right? So up until the end, it's the same thing. But the other way to avoid doing necessary and sufficient parts is by stating the fact that either the thing you have to prove is a image in the mirror of the other statement. So in this case, by replacing the variable or the matrix A with the matrix B and the matrix B with the matrix A, you will notice that nothing changes.
Oh, I see. So like, for instance, if I can just prove that A and B are interchangeable, then this statement literally turns into this one.
Yeah, and they are interchangeable. It's very clear they are. So you would only need to prove one direction, and the other one is literally the same thing, but replacing the matrix with the other.
Okay. I think I'm starting to get this proof thing.
Yeah.
Okay.
That's an important part, so you don't do too much work.
Yeah, we don't want to do too much work.
Yeah, especially when you're on a timer.
Yeah, and yeah, you bring up a really good point. What is the time? This came from a competition question, which I think I have the full thing. Yeah, I have it here on Discord. Yeah, this is it, which was 4 questions. Yeah. How much time do you get?
If you look at the bottom, it says time of like 4 hours.
Oh, 4 ore. Okay, 4 hours. Okay, wow.
Yeah, and each problem has 7 points at most.
Gotcha. Okay, each point's out of okay. So 4 hours, 4 hours for 4 problems, but obviously, not every problem is going to take the same amount of time. I remember you saying that like one problem is like incredibly long, right?
Yeah, like the last one, you either do it in like an hour and a half because it's very long, it's very lengthy, and if you look at what it's asking, it's still like hard to understand, like grasp what it's asking, right? And surprisingly, the last and the first problems are pretty long. The first one is long because it's a lot of calculations.
Gotcha.
Right? So most of your time should be focused on the first and the last one in this case.
Mm-hmm. We picked the third one because I like matrices, and you at least knew that. Oh, I might be able to understand this one. Also, like from time constraints. Yeah. If it takes you an hour to do it and you already know what you're doing, imagine how much time it would take for me to do it and I don't know what I'm doing.
Yeah, like kind of, yeah.
Yeah. Okay, so let's start here. So this is our starting point, right?
Yeah, exactly. So we did this. This was pretty intuitive. Like when you have variables, you just tend to move them to one side and see what they factor out to be.
Yep, I agree.
In this case, they factor out nicely.
Mm-hmm.
Yeah. A trick in actually not a trick. A good like for like a habit you should have when you work with matrices, especially with multiple matrices at once, is taking determinants and traces of both sides.
Okay.
Yeah.
What's the difference
So
between a determinant and a trace, though?
So the determinant of a matrix, this is the 2x2 matrix. It says that they are 2x2 matrices. The determinant is actually just the difference of the product of the diagonals.
Right. Okay.
I think that's pretty clear.
That's pretty simple. Yep. Exactly.
Yeah.
Right. The determinant of like A, B, C, D is just AD minus BC, right?
Yeah.
Okay. But then the trace, is that where you just multiply the diagonals?
You add up the diagonals.
Ah. In any order?
Well,
or I mean,
yeah.
sorry, just as it is.
The diagonal.
Okay, just A plus D in this
case. The main
case.
diagonal, yeah.
Gotcha. Okay.
There is a difference between the determinant and the trace if you are familiar with the characteristic polynomial of a matrix.
Characteristic polynomial of a matrix. I'm not. What's that? It sounds like a fancy word for something.
It is, but it's like mostly. I think you know eigenvalues, right?
I do. I know like determinant of like A minus lambda I is equal to 0. I know that.
So what is the determinant is a function, right?
Correct.
So what do you get when you equal a function to 0?
What do you get when you equal a function to 0? You get factors.
This is more like mathematical and like how much do you know about theory, right? So I
don't know that much about theory, unfortunately. So
okay,
here,
so
tell me.
When you have an equation,
yes,
not equal to anything, that is called an expression.
Good. Okay, I understand that. Yep.
When you have a function or an expression in this case equal to a value or equal to 0,
right,
you get an equation.
Okay.
So there's a difference, expression and equation. In this case,
equations have solutions, I guess.
Equations do have solutions, and the solutions of this determinant equating to 0, you get its eigenvalues of the matrix A.
Okay,
right?
Good.
So,
which are these?
Intuitively, the determinant has to be a polynomial.
Sure.
Right.
And it's usually, I guess it's A minus lambda, what is it, D minus lambda, and then minus CB. Is that kind of how that works? Or yeah, CB. Wow, thanks for the sub, Pen. Shout out to Pen Center. Intuitively, the determinant is the goat. Pen Center says that the determinant is the goat. Okay.
Right, so let's actually get what this determinant would be, because we are working with 2x2 matrices, so this should be very simple.
Yes.
So let's just say the matrix A. This is separate from our question right now.
Yeah.
Let's
This
just
is a
say the
separate
matrix,
thing.
Yeah. Let's just say the matrix A is A, B, C, D, right?
Gotcha. Yep. We're gonna call this a side quest.
Yeah,
Okay.
sure.
A B C D. I agree.
Yeah. So what would be A minus lambda I?
I think so. A would be, so it would be like A minus lambda, B, C, D minus lambda, right?
Yeah, and I'd like for you to calculate this determinant.
Sure. I think that would be this, right? A minus lambda times D minus lambda, minus C times B. I think this is what it would be, right?
Yeah, so expand it, please.
Oh, expand it. Oh, he wants me to expand it now. Okay. Okay, but here we go. But expand. All right, let's expand it. So that would end up being AD plus lambda squared, and then okay, minus lambda D minus lambda A. Yeah? Oh, I see. This is a polynomial. Lambda squared,
Yes.
and then minus lambda D plus A plus AD equals 0.
So, and what do you know about A plus D and A? Is it AD?
I think it's AD, or wait. It's AD minus
minus
CB. I forgot about the CB part. Uh oh.
Huh? Yeah.
Okay,
Minus
yes.
BC, yeah.
Minus BC. Okay. Yes.
Yeah. So what do you know about A plus D in the context of it being in a matrix?
A plus D is the trace,
Yeah.
right? Yeah. Okay,
And,
so this is
and what
the trace.
What is and what is AD minus BC?
Oh, that's a determinant.
Yeah. And that is the characteristic polynomial of the matrix.
Oh. So you're
in
saying
this case for a 2x2 matrix, yeah.
eigenvalue squared minus the trace of A plus the
Lambda.
determinant of A.
Yeah, don't forget the lambda.
Oh, I forgot the lambda.
times
Yep.
trace.
Good. Yep. Sorry, let me move this. Oh
Yeah.
no, move the T as well. Is all equal to 0. Got you. Cool. That's the characteristic equation of a matrix, I guess, right?
Of a 2x2 matrix, yeah.
Okay, that makes sense.
It gets more complicated if you go up to like 3x3 or a 4x4 n by n.
Yeah. We don't need to get scared.
What you should know is that when you have an n by n, we've already established that a determinant is a polynomial regardless of the dimension of the matrix. So you could be n by n matrix, and the determinant of a minus lambda I should be a polynomial.
Okay.
Right. So in the case that we have an n by n matrix, and this is just like a fun fact to know, the last term, so the term that doesn't have any lambdas in it, right?
The BC term?
Yeah.
Or
in
the
this
AD
case,
minus BC. Yeah, this term.
let's see that. Yeah, sure. That will always be the determinant of A, right? So the last term, the lambda-free term,
Yeah.
will always be the determinant.
Regardless of what the eigenvalues of.
Regardless of the dimension of the matrix.
Oh, regardless of the dimension. Okay.
Right.
Got you. Okay.
And similarly, so will the trace remain the same. So when you have, let's say you have lambda to the n minus lambda to the n minus 1 times the trace, right? This will always be how it goes.
Okay.
So the determinant and the trace remain the same in the same positions at the same coefficients.
I see. Okay.
Yeah. One more thing that I wanted to say, if for instance, if this equation has two roots, lambda 1 and lambda 2, correct?
Yes. Yeah, it's a quadratic. I mean, I guess it could have one root, right? There's a possibility for it having one root.
A quadratic equation never has a single root. It always has two roots.
Oh, they're just
but
repeating.
It can have one solution. Yeah, it can have one solution but two roots.
I see. Yeah, most people be like, oh, there's only one solution, or there's no solution. But those are complex. I get it. Okay. Yes, I agree. There's two solutions.
Careful, like, for any amateurs, if it asks, like, if a question asks you for the roots, don't say there's only one. If you have a quadratic, there's two, and it repeats.
We call these degenerate roots.
Yeah.
Yeah. Okay.
So let's say then if lambda 1 and lambda 2 are the roots of this equation, then, and let's suppose for the case of this argument that they are different, so they are both solutions.
Okay, so let's say lambda 1 and lambda 2 are roots, and they don't equal each other.
Yeah.
Okay.
It's not lambda 2. Yeah.
Got it.
In this case, lambda 1 plus lambda 2 is going to be the trace. This is just Vieta's formulas.
Oh, okay. Is equal to the trace of A?
Yeah. And lambda 1 times lambda 2. Can you guess?
Is that
what this
also is that equal to the determinant?
Yeah. It is
Oh,
equal to the determinant.
what? Oh, I'm learning so much cool shit about matrices today. I feel like I just took the blue pill.
We can actually generalize this. We can generalize this. For an n by n matrix, the sum of all eigenvalues is the trace, and the product of all of the eigenvalues is the determinant. So if you have n eigenvalues...
So for n by n matrix, we can say this of lambda n is equal to the determinant, right?
Sure, yeah.
And then this lambda n is equal to the trace. Okay, cool.
It is. Yeah. And yeah, this is... I don't think we use this, but this is just fun to know. This is very, very useful to know.
Oh yeah, very
especially
useful.
Especially the characteristic polynomial.
Okay.
Yeah. So if we go back to...
Let's go back to what our original
the question. Yeah.
Jeff says,
So
can we
we don't
challenge the
believe-
Romanian with questions?
Yes, you can challenge me.
You
Sure.
can challenge. Yeah, challenge the Romanian. Challenge him. Okay.
Right. So what I did here, I have this equation here: AB times AB plus BA is equal to the zero matrix.
From here, yes, we got to here. I agree with that.
Yeah. Use calculus of variations to show grid surface the shortest path on the surface of the sphere. I don't know calculus that well.
Yeah.
That is a problem.
Not yet. He's gonna learn calculus eventually.
You can ask me stuff up to like calculus maybe 2, but even then I might like struggle. Yeah, I'm not that
Nerosky's
crazy.
just a genius in the things that he's been exposed to. He hasn't been exposed to like high level calculus yet, but I'm sure he's gonna like beast it when he gets to it.
Yeah, soon enough.
Soon enough. Okay, so we came up with this. I agree from
We
the
did.
factoring from before.
Yeah, sure. So
And then this was
I
the
do
argument
have
where
formula
you said that determinant of AB plus BA must be equal to 0. Otherwise, if it wasn't equal to 0, then you're saying AB would be 0. Right, because you either need this to be 0 or this to be the 0. So if this one is not 0, then this would have to be 0.
Yeah.
But then you would say that the determinant of AB plus BA has to equal the determinant of BA. Because this is 0.
Because
and
it
then,
is 0, yeah.
And you say this is like not possible. I can't have the
that's-
determinant of something plus anything, even if that thing is 0, still be the determinant of the original thing? Is that kind of the statement?
So, no. If you follow it carefully, what I said was if AB plus BA is 0, then the determinant obviously is 0, right? suppose it's not 0.
Yeah. Okay.
Yeah, suppose it isn't 0. So then AB must be 0.
Oh, okay.
And the determinant of AB plus BA is going to be the determinant of BA because AB is 0.
Yeah.
But the determinant of BA is 0. Because it's the same as the determinant of AB.
Sure.
So determinant of AB is equal to determinant of BA. It doesn't matter the order you have them in.
Right, okay.
Yeah.
I
and
see.
this cannot happen because we suppose it is not 0.
Not equal to 0. Got you. Oh, that's
yeah,
a cool...
which is, yeah. That's also the sign for a contradiction, if you didn't know. That's how you signal to
There's like
whoever's reading that.
fancy swords.
Yeah, that's contradiction. From what I know.
Sugar-
You can also say like, yeah, like this, kind of. You can also draw like 2 arrows pointing into each other. I've seen that as well.
What's up, Ramton?
Hey, how's it going? I was just joining to say how are you doing?
We're
I
doing
was
good.
just joining because I wanted to also learn some of these stuff. Like I see you're
Good.
doing
Yeah,
proofs
come
in
learn.
linear algebra.
Yeah.
Yeah, it's
Oh, very nice.
it's a competition math question from I think this year or recently, and
Okay.
we're going through the proof of it, and I'm learning a lot about traces and determinants, and this is actually related to what we're going to go over tomorrow, Ramton, right? Because this is proof by contradiction. This is like one of the proof techniques.
Yes, this would be exactly. You assume the opposite is
Yes.
true, and then it creates a contradiction.
It
as
creates
you said.
contradiction, so yeah, it can't happen.
Yeah.
Yep.
Okay. Very cool.
So
Okay.
the next
so
step
we
took-
determined that this has to be 0. So then
Yeah,
the next
we-
step
we
you
did
get
this
to
already.
here. Oh, you okay? So
I
you
think-
square it.
I think about squaring it because why do I square it? Because I have AB squared, AB squared A, BA squared B, and BA squared, which is all that we have in our question. So
I
if you
see.
scroll up,
Yeah.
this all
That's-
shows up.
Right. I see. This shows up. This shows up. This shows up. I see. So
Yeah.
that's the inspiration. The inspiration is
That's why I did that.
cool. Okay. Hey, man. You're like, oh,
Yeah.
well, this will like start popping out all the shit I want, anyways. Okay.
Yeah, and so why not square it? So I noticed that AB squared plus AB squared A is 0 from what we supposed is true.
Oh, this
So
was
we
the
suppose
suppose.
the
Right. Yeah. This was the
Yeah,
original claim.
suppose. Da.
Got you. Okay. Okay. And then you go
Yeah.
on to
We
say
take-
that the trace.
We take the trace of both sides.
Okay.
Yeah.
So that's the
We can
trace of
split-
this.
We can split the trace though. Yeah.
Okay. There's some algebra of traces. And then also the
Yeah.
trace of 0 is just 0.
Exactly.
Okay.
Now take the trace on what you would like to find. So
We
instead
want
of
to prove
AB
that
squared
this
plus-
equals 0, right? This is what we
Yeah,
want to
so-
prove, right?
Yeah. So let's take the trace of that as well.
Okay. Right. So we take the trace of
So-
that.
Yeah.
Okay. And then you expanded it, I guess is what
Yeah,
happened
because I
here.
don't know anything about it. Yeah, we don't know anything about it yet. so we
Trace of
expand.
BA. So I get this. Wait. Why did this turn into ab? Is it because traces you can interchange the variables as much as you
Yeah,
want?
yeah.
Okay.
I believe. Yeah.
So regular multiplication with matrices and whatever vectors, you can't just randomly switch the order. That's a commutative property, I guess. But
Yeah.
within the trace, you can.
Within the trace and within the determinant, yes, you can.
Okay. Cool. So you rewrite this one instead of saying the trace of BABA, you call it the trace of ABAB, and then this one you end up calling instead of A squared BB, you call it, or instead of BA squared B, you call it A squared BB. Okay. Cool.
Yeah.
Which
So
I
we,
see.
We eventually reach. Yeah.
And then you so then you're like, but wait a minute, I can just switch the order as much as I want anyways. So fuck it. I'm gonna
Yeah.
make it look like the original one as well.
Which is 0 because we know that.
Sure. Yeah, okay.
Yeah. So we found another thing about what we want to prove. So we are on the right path.
I agree.
My man.
We're on the right path. I like this. Okay.
Right. So the next step is just. Of course, we have the trace of the original, like the thing we squared of 0, and now we can apply something called the Cayley-Hamilton theorem.
Ooh, I've never heard of this one.
So
Okay.
this is why this is the inspiration for me explaining the characteristic polynomial before. So if you can scroll back, so it makes more sense.
Which one? Which was this the characteristic
This,
equation?
right? So zoom. No. Oh yeah. That's right. That's right. Let's zoom into
This
that.
one? Okay.
So any characteristic polynomial, and this is why it's called characteristic, and it's not just the polynomial of a matrix. It's the characteristic polynomial of matrix A, since if you replace lambda, like the eigenvalue, with the matrix A, so if you'd call this the polynomial P sub A,
Okay.
right? So let's say P sub A of lambda, in this case,
Okay.
is this.
Is equal to this. Yeah.
Then P sub A
Okay.
of matrix A
Yes.
is going to be the zero matrix. So any
because-
matrix satisfies its own characteristic polynomial.
Because what I'll get matrix A squared, which I guess is the determinant squared, right? And you're saying minus A trace A.
You can prove this at like a small dimension level, since if you want to prove this, you can.
Mm-hmm. Is this so when you square? Oh, this is just the matrix multiplied by itself. Oh, okay.
Yeah.
Uh-huh.
Yeah, nothing fancy.
Nothing fancy. Okay. And
Yeah.
then this is
So-
multiplied by the trace, which this
Yeah.
is a scalar then, right? The trace of A? Yeah,
Yeah, it
determinant
is a
also
scalar. Yeah.
Okay.
Also scalar, yeah.
I had a quick question
Yeah.
for
Sure.
Nerosky. For the Cayley-Hamilton equation, does the matrix need to be invertible in order for it to satisfy the equation?
No, any matrix satisfies its own characteristic polynomial.
Oh, okay. Okay.
Yeah, regardless
even-
of.
Okay. All right.
Yeah,
Is that
that's
because
what actually
it-
makes it so powerful.
If it's
Oh, yeah,
invertible,
okay, so-
it means the determinant, right, is not zero.
It's not
Yeah.
zero, but the determinant can be zero, and it still satisfies the equation. And you will see that
Oh.
there's a few fun properties I want to give, and thank you, Ramton, for reminding me.
Okay.
I will continue like this list we have already here.
I love this
later on.
list of. Okay.
Yeah. Now that we know this, right? So any matrix satisfies its own characteristic polynomial,
Okay.
right? Regardless of dimension, regardless of anything. It's simple in the 2x2 case because it's like literally replacing.
You can just look at the elements. You can say, oh, cool,
Yeah.
80 times this, BC times this, like whatever. Yeah.
Yeah, it gets more complicated later on. You rarely need the Cayley-Hamilton or the characteristic polynomials for a 3x3 matrix. You can deduce them, since you can still calculate the determinant of a 3x3 efficiently. There is a relatively simple method, but it still is complicated and time-consuming to do that.
Right.
You can also do it by induction for any n by n matrix, as long as you make the assumption.
I would be so pleasantly surprised if you managed to do that, because it involves like the adjugate of a matrix.
The
later
adjoint?
on, and
Oh,
adjoint. Yeah.
adjugate. Yeah, adjugate. Yeah. Interesting.
Is that like the
oh, yeah.
adjunct conjugate? Adjoint conjugate is the adjugate? I've never heard of the adjugate. What's the adjugate?
No, adjugate is like, I forgot. It has to satisfy like a weird property. I think Nerosky might remember it, since he mentioned.
So, yeah, the adjugate is. I'm not sure if I'm saying it right, because there's a different name for it in Romanian, but it is basically A star.
Yeah, you're definitely correct. It's like the adjugate of A is the transpose of the cofactor matrix.
Yeah, exactly.
Yeah.
Okay.
That's what I'm. Yeah.
I know this one. I know
So,
like A
yeah.
A with like the Jesus crossed on it.
Yeah,
That's
that is the
adjoint, right?
transpose.
Or transpose,
Yeah.
right? And then there's stuff like adjoint and like self-adjoint and like all these things. And I'm just like, wait, what?
You're not that guy, pal. Trust me. You're not that guy.
Okay. Yes, Taco Cat.
So-
The chess tournament is at 9 p.m. Your time. Okay. All right. So let's get to. Do we have enough to learn about Cayley-Hamilton yet, or do we need to learn?
Yeah, we
couple more things?
we have enough. Yeah. So since we've learned that any matrix satisfies its own characteristic polynomial equal to 0,
Cool.
we can replace the whole AB plus BA squared into this, right?
Into the characteristic equation here. Yeah.
Yeah.
So I'm saying
because
P-
AB plus BA is a matrix, yeah.
P of AB plus BA is kind of what I'm saying. Here, let me like pull this
Yeah.
on here. Right.
If you want, you can. I didn't do this because I was in a hurry to finish it. You can denote AB plus BA to be like a matrix C, for example, so you can see it easier.
Okay. Oh, if I say I say here you're gonna say like let AB plus BA equals C.
Yeah. And then,
then-
C squared.
Yeah, what was it? It was P sub lambda of
P sub C of C.
P sub. Sorry, what do we call it? P sub. Okay, P sub C of C. Yes, there we go.
Yeah, P sub C of C.
The characteristic polynomial of C on itself. Okay, and then that's going to be equal to C squared minus C trace of C.
Yeah.
Plus the determinant of C. I think.
Careful.
Right?
Multiplied by I2. See?
Multiplied by I2. Why? Why multiply by I2?
So notice how in like so.
Because
a
the answer
matrix
needs to be O2. I get it. Your answer needs to be a 2 by 2.
Originally, this is very ridiculous, but this is how matrices work. I'll let you finish.
I see, because this will turn it into a 2 by 2. C squared is still a 2 by 2, and then you're saying, but I need to multiply this by I2 in order to get O2, because these all need to be 2 by 2 matrices. Okay, I got it. Go on. What were you gonna say?
Exactly. I was gonna say this I2 pops up because it is the identity equivalent of 1, and in the original expression, the determinant is actually multiplied by 1, right?
Okay.
So its coefficient is 1.
Oh, okay, I see.
So yeah, that's why the I2 pops up there.
All right.
And if you notice, this is exactly what I wrote as well, just with AB plus BA squared.
Good. Okay.
Minus
Cool.
trace, yeah, whatever.
Oh, go back. Sorry. But then we said the determinant of AB plus BA was equal to 0. Right. That was our initial claim up here.
Recall this. So let's stop for a moment. What happened? What do we want to prove?
Yeah, what were we trying to prove again?
Yeah. This is something you have to do every time in a proof.
You have to like take a step back.
Yeah, wait a minute. I did a lot of stuff. It all looks good. Let's see how do I like bring it together.
I agree. So this is what we want to prove eventually, right? Was this?
Yeah. We eventually want to prove that it is AB plus BA squared, I believe, should go to 0.
We want to prove that wait. What? Sorry, say that again.
So look at the expression for AB plus BA squared.
Yes, I see. This, okay.
We already know that the first part of the right hand side is 0.
We already know this is 0.
By our assumption. Yeah.
Exactly.
We want to prove that the other part is 0.
Okay, got you. Got to prove this equals 0.
Because we want we want one to be the negative of the other, and this happens
and
if
then
only
because
the
determinant of AB is equal to 0, AB plus BA squared has to also be equal to 0. Is that what we're saying?
In a moment, if you look at the characteristic polynomial.
I'm getting ahead of myself. I get it. I'm getting ahead of myself. Yeah, wait.
Yeah.
Just because of the determinant's equal to 0 does not necessarily imply that thing squared is 0.
No, because and you can see why in the characteristic polynomial why that isn't true. If the determinant is 0, the scroll to the right a bit.
If the determinant is 0, you can still have the trace and this cancel each other out or something, right?
Yeah.
Gotcha.
Yeah, so you're gonna move C trace C to the other side, and then
C squared equals C trace C.
Oh. Yeah, I think you're gonna have a cool identity. Can you draw an arrow up from the characteristic polynomial?
Okay. From up here to where?
Yeah, if anywhere you want, like if the determinant is 0, If so,
Okay.
if that C is 0,
Yes.
what happens?
Okay, great. I like this. Okay, and then we're gonna say then you would have c squared minus c trace c is equal to 0. So I could move that over, and I would say c squared is equal to c trace c. And then
Can you
I don't know.
multiply this? Can you multiply this equation by C on both sides?
Do you want me to get c to the third?
Yeah, sure.
Okay, sure.
I
So
want you to
that's
see a pattern,
c to the third equals c trace c times c.
which is just C squared.
Oh, because trace of c is a scalar, right? Okay.
Yeah,
Sure.
exactly. It doesn't matter where you multiply it.
Okay, all right, that's fine. Okay. I get very careful. I'm just like, wait, am I allowed to multiply it on that side? Okay,
Yeah.
trace c. Oh, okay, so
But
that
what
tells
do you know,
me
What do you know about C
Yeah.
squared?
c squared is equal to c trace c.
So let's plug that back in.
Oh my god, wait, okay, what? Oh my god, this is... Dude, this is where math just starts getting wacky, dude. I'm like, wait, what? It's like, yo,
You
dog.
can do this, by the way.
Do you know the meme, the exhibit meme? Is that a little too old for you? Do you know who Exhibit is?
I don't think I do.
So he had this TV show called Pimp My Ride, where they would like cut people on the show would give a car to Exhibit, and then he would turn it into something ridiculous based on like what they like. And the meme joke about it is I'll pull it up. It's really funny. It's yo dog.
Very glad that you're playing it up. This is like the millennial show everyone
Yeah,
watch.
this was, yes. So this is the meme of Exhibit, and he says like, yo dog, I heard you like cars, so we put a car in your car so you can drive while you drive. Because what he would do, like say,
I actually do know this.
this is super old, which it's funny how like
Yeah.
sometimes like parts of Eastern Europe get our culture but like 5 years delayed. So even though you are younger, you probably maybe got this just because it was delayed.
Yeah, I did get this like in 20, I don't know, like maybe 2012. I saw this.
Yeah, it was, so Pimp My Ride examples. So for
Maybe-
instance,
maybe later,
if
I don't know.
if someone liked if someone liked juice, they would put like a fucking juice bar in the car, and they'd be like, yo dog, I heard you like juice, so we put a juice bar in your car so you can drink juice while you drive. And
I remember there was one episode that I remember, and that
Yeah.
was actually good. They took this like van and they put like a bunch of like gaming and movies and all that stuff. They just made like a man cave almost in the back of this van, and that one looked pretty cool.
so that's what this reminds me
Yeah.
of. It's because here in this math, it's like, yo dog, I heard you like c squared, so I'm just gonna like put it back in again. So-
you're not gonna believe what I'm gonna do next.
Oh god, are we gonna do it? Wait, 1 second. Okay, so now I have c cubed is equal to c. Am I gonna multiply it by c again?
Yeah.
Oh, you're a monster. You're a
You're
monster,
actually
dude.
You're gonna say by induction. I believe you can see that.
Oh, I think I'll start seeing the pattern.
If
See-
you don't mind, I don't want to like step on your toes, but I had a question. Couldn't you have like factored out a C matrix from the first equation, from the left
Yeah.
side, and then say that C times C minus trace of C times the identity is equals to 0? So it kind of proves that C has to be like a, what's it called? A diagonal matrix.
That's a nice way. Yeah, I believe so.
Okay.
I'm gonna try to understand that, Rem, at the end of this. But yeah, hold on to that. So wait, I think what I understand with my little brain here.
Is that c to the fourth is equal to c times the trace of c cubed. So c to the n is equal to c trace of c to the n minus 1. Is that kind of the...
Yep.
That's the, I guess, induction or something?
Yeah, this is by induction.
Beautiful.
I'm gonna shake you up a bit at this.
Oh, no. You're not that guy, pal. Trust me. You're not that guy.
All right, what are you gonna do to me?
This is identical
man?
to saying that you get this exact expression. You get it if the rank of C is equal to 1.
Ooh, okay. Okay, I gotta remember what rank is. Rank is when you RREF it, and it's how many pivot columns you get, right?
That's a very complicated way of thinking about the
Okay.
rank, but
All right.
yes.
You. What's the correct way to think about rank? Rank of a matrix. What's that? Is it like the number of independent columns or something?
Yeah, that is the better way to think about it. Yeah.
Okay.
So how many independent rows or columns do you have?
Got you. Cool. All right, I like that. Okay. Number of linearly independent columns or rows, I guess.
Yeah.
Okay.
Rows, yeah.
And sorry, what was the statement about the rank of a matrix and something in one?
So if the rank of a matrix, so in this case rank of C,
Yes.
is equal to 1,
Yeah.
then it's equivalent to C to the power of n is equal to C times the trace of C to the power of n minus 1, which is what we just said before.
Oh, okay. So this is only true
So
if
it's-
the rank of
yeah.
C is equal to 1? Is that what we're saying?
No. If the rank of C is equal to 1, we also have this property because the determinant is going to be 0, I believe.
Okay. Yes, I see. If you have a matrix where, I guess, you only have, like, this, right? And everything else is zeros. Then, yeah. The determinant will be 0. Okay. Oh! I see what you're saying, Nerosky. Sorry. If the rank of C is equal to 1, then the determinant of C is equal to 0. And that's what we said here, right? Was that if the determinant of C was equal to 0, then all this shit is true. Got you. Okay, cool. So this implies this. Again, I had to zoom out and be like, wait a minute. Wait, what? Where did we even come up with this before we were talking about like exhibit and like cars? I was like, oh,
Exactly,
it's
yeah.
because we said the determinant of C was 0. Got it. Okay.
And another fun thing about if rank is equal to 1, let's say an arrow to the right side because it doesn't like have any.
I love all these little
correlation with
math
what
side
we said.
quests. I'm learning things. Okay. All right.
Yeah.
Side quest.
If the rank is 1, then the determinant of I plus A, or I plus C, for example,
Determinant of I plus C
is equal to 1 plus the trace of, yeah.
is equal
I
to
plus
1
C
plus
is
the
equal to
trace of C?
Yeah.
Huh. Oh, where this is... Sorry,
These are
I should...
very powerful. Yeah, these are very powerful in proofs.
Fascinating. Side quests. If the rank is equal to 1, the determinant of 1 plus C is... Okay, cool. I'll trust you on this. I'm sure we could prove it another time, but okay. I'll assume that's true.
Yeah, this is proven. Yeah, it's very simply proven by diagonalizing matrix C.
Okay.
So if you get a matrix of passage, say call it P, in the general linear group of dimension A over the complex numbers, such that the matrix PA p to the power of minus 1 is upper diagonal.
Okay.
At most, one entry of that matrix is non-zero, and all other ones are 0. So then, that basically means what we just said.
Okay.
I don't know if that made sense.
Oh, I see. Wait. Because 1 would be this part, right? Is what we're saying?
Yeah.
Oh, wait. Sorry, this is not
At
identity
most,
1.
one is non-zero,
Right.
and all others.
Gotcha. Okay,
It's one. It's just one. Yeah.
It's just 1. I see. Okay, if the rank of C is equal to 1, then, okay, then you can make at least one entry in your I get it, with your upper diagonal matrix that is like non-zero, and then the determinant
And the other
of
ones
adding 1 to that. Oh, I see. Basically repopulates all the other stuff. So the trace of what you originally had plus 1, because all the other determinants would go to 0. All the other like little side determinants you do will still go to 0. But putting all the 1s here on the diagonal like saves the 1 row or column that is not 0 from like not dying, I think.
Yeah. There's also. Do you know vectors? Do you know vectors in?
I know what vectors are, yeah.
Yeah, you can rewrite. So since matrix is of rank 1, you can rewrite it as UV, like the product of two n by 1 and 1 by n vectors.
Oh, I see. Yeah. Okay. So like a matrix that, let's say, for instance, is yes, n by n. This is the same thing as an n by 1 multiplied by a 1 by n, right?
Yeah.
And this could be like vector A, and then this could be vector B. Okay, cool. I understand that.
Sure. So if you just rewrite it as the product of these two vectors,
Just call it like
you literally have a one-line proof. You do have a one-line proof. Like
so you have C is equal
go
to
through,
AB.
like,
Is that what you're saying? Like C is equal to AB?
I don't like that you're using big letters because those usually mean like matrices. not
Okay, so
vectors.
let me use small letters. No, this is good. I need to know the lingo and the jargon. Okay, let's use small letters here. Okay.
And yeah, don't put the vector arrow over them, please.
Don't put the vector arrow on them. Okay.
I think if
We
you put
call
the
them
vector,
vectors, but
yeah, if you put the vector arrow, because one of them has to live in the dual space, right? If you put it, that means that they are in the
What's
same
the
space.
dual space? What? Dual space? It's like the upside down?
Yeah.
What's a dual,
Dual
space?
space is like essentially it's the row version of the matrix. Yeah. So like the column matrices live in one space,
Okay.
and then the dual matrix lives, or sorry, the row vectors lives in the dual space.
Okay. I get it.
Yeah.
You're talking about like the vertical stuff and then the horizontal stuff.
Yeah. The only reason I learned this recently because if you put two vectors together, that's called a bivector, and that's used in Clifford algebra.
Ooh,
Yeah.
big red dog.
Yeah. That's right.
Sorry, I have to introduce my humor. Okay, so all right, so if C is equal to AB, Nerosky, yeah.
Yeah.
What were we, how's this a
Then-
one line proof?
So then, what do you want to prove? You want to prove that the determinant of I plus C is equal to 1 plus the trace of C. So let's just rewrite
Yes.
the determinant.
Okay.
So it's going to be the determinant of I plus AB.
Oh, I plus AB. Okay. Oh, I see. Is equal to
Yeah.
1 plus the trace of AB, right?
Yeah, but that's too quick because it's going to be it's not that
Okay, it's not that quick.
Surprise, motherfucker!
Okay, what do I
Yeah.
gotta write? Sorry.
No, it's going to be 1 plus BA.
1 plus BA.
Does that make sense? This is a okay.
Where does that come from? Sorry.
So 1 second, let me give you a screenshot of.
All right, good. Screenshot coming in.
Oh, also, a quick question, Nerosky. I wanted to double check. If two matrices multiply to each other and give you the zero matrix, does that mean that at least one of them is a zero matrix, or does that mean that at least one of them has a determinant of zero?
So
I think it's the
I
second.
believe that means one of them has to be the zero matrix.
Okay. Because I feel like if that's the assumption, then for some reason what I was saying before doesn't work. That means that either C has to be zero or C can't be zero. But then I think the determinant would make sense. Anyways, but I just thought to ask that.
Yeah.
But,
Yeah, no, I believe it has to be zero. Like in the same way you're thinking, like since 1 is the equivalent of the identity matrix, like in numbers versus matrices, the same way that 0 is the equivalent of the zero matrix, right? So you couldn't have like a number A multiplied by a number B equal to 0 unless one of them is 0, in the same way that you cannot have two matrices multiplied together equal to 0 unless one is 0. Like the zero matrix.
I see.
All right, I got your screenshot, Nerosky.
Yeah.
What do you want me to
Yeah,
do?
this is what we're basically doing. A is I in this case, and
Okay.
UV to the power of like, UV transpose is
Yes.
like our AB. because
okay.
B is basically like a how do I say this? It's a
I see. These
It's
were
also
two. These
an
were
n by one.
these were two column vectors, and then you made it to a column vector times a row vector.
yeah, exactly.
Right? Okay, gotcha. I understand.
Yeah,
So, yeah,
and it's-
the transpose is kind of like by design.
Yeah,
we already called this a
if you have
line.
yeah, exactly.
Okay, cool. Okay, so the matrix determinant lemma states that the determinant, right? Okay, cool. So in this case of I plus AB is equal to 1 plus B I inverse. Wait, but I inverse is just I, right? Okay.
It's just I, yeah.
Oh, which is just BA.
Exactly. Times
Okay.
the determinant of I, which is 1. So
Times the determinant of the identity matrix, which is just 1. Okay, cool. All right, so we just left that. We just left that, yeah. Okay.
And
So what do we can do with this now?
1 second. So I believe you can take trace of both sides now.
Okay. Let's trace both
The
sides.
trace of the determinant is just a determinant because the trace of something that is in a matrix is
Right.
just nothing.
It doesn't do anything. Okay, so trace of that.
Yeah.
Trace of that. So this just becomes, yeah, cool. Determinant of I plus AB is equal to the trace.
Is 1 plus the trace. So you can pull out the 1.
Oh, because the trace of 1 is just 1. Okay, sure.
Exactly.
1 plus the trace of BA.
Which is the
Okay.
trace of AB.
Which is the same thing as the trace of AB. Right, okay, because, yeah, traces are...
Yeah.
Oh, and now you just... This was the thing I wanted to jump to, right? Saying that the determinant of AB is equal to 1 plus...
Trace of A. Yeah,
Trace.
or trace of...
Wait, okay, so sorry. This is trace of AB. Yeah, right?
Yeah. And which is basically what we wanted to show.
Oh, okay.
Yeah, because C is AB.
Got you. Okay, cool. I see. And that came from this. Wow. And that's like not even getting into the nitty gritty of how the matrix works. That's
Yeah,
just...
This is very nice, yeah.
Yeah, sorry, what does it mean when it says a lemma? Is a lemma like a law? What's a lemma?
A lemma is a smaller theorem.
Okay, baby theorem. What makes it a baby
Yeah,
theorem?
kind
It's
of.
just because it doesn't say enough cool shit, or like what makes it a baby
I'm
theorem?
not sure. Like I just know it's like it's something you prove along the way, and it's like it's not so significant as you like to call it a theorem, right?
It's funny because when I was coming up with names for this stream series, I was using like ChatGPT. I'm like, come on, let's come up with like some cool ideas. Its idea was the Gilded lemma, and I was like, man, that sounds kind of lame though. Gilded lemma? Lemma sound lame, dude. What?
I think if I'm not mistaken, is that a theorem has to have all the steps to a proof, and it cannot be referring to another theorem.
Oh, it
But
has
a
to stand on its
lemma-
own.
Yeah, and I think a lemma uses the result of a theorem to prove something else.
Interesting. Yeah, Hamiltonian dynamics
Yeah,
says not enough
yeah.
aura to be a theorem. It doesn't have enough
Basically,
aura.
yeah, basically that.
Okay,
Yeah,
cool.
that's basically it.
I didn't know that. All right, I learned another thing today. This is dope. Okay, so because of this,
So,
which I guess you're just
finally we
supposed
can-
to just know this. We then proved this, which great. We then proved this. So let's get really far out again. Like, what was the whole point of this again?
This was just for fun.
Oh, this is just fun. Okay, side quests for fun. Okay, cool. That's fine. I like side quests for fun. I love these. These are great. Yeah,
This
side quests are
actually
fun.
shows how much like linear algebra is intertwined with itself, right?
What's
So
crazy,
you can-
Nerosky, is that again, you say you don't know as much calculus because you haven't really taken as much of it yet, but usually in the U.S., people don't touch this linear algebra until after calculus.
I learned this in like second year university, and I was already doing like triple integrals in high school. So that's why I'm like
Yeah, I
very
can-
impressed by your
Yeah,
knowledge.
yeah, yeah. Yeah, the order of knowledge is interesting. I guess you don't need calculus to learn this, right? We're not really doing any calculus concepts.
I find that the curriculum is like perfectly balanced in the way that you don't need anything that you shouldn't learn. Like you learn everything that you can at the moment that you're supposed to learn it. Like
I see. There's no prereqs
anywhere.
Yeah,
There's absolutely no gaps in anything at any point.
I think that is smarter, because then I would argue that learning calculus 3 but not knowing linear algebra can be a pain sometimes. Because then you start getting into like vectors and spaces and bases, and I'm like, what the fuck is this shit?
Yeah, it doesn't make sense without the basic understanding of linear algebra.
I think linear algebra just sounds scary.
Honestly, for me, I didn't even understand. Like when I was taking linear algebra, I was just getting absolutely destroyed. But the thing that made me understand linear algebra more was Hilbert spaces from quantum mechanics. But it has further restrictions. But you could actually see something that had like physical meaning.
Yeah, I think that's why I did so badly in quantum. But go on, Nerosky. Sorry, say it.
The difference is I don't know what that is.
Yeah, it's okay. It's a linear space that is has to be closed under dot product, but you don't have to worry about it.
Oh, okay.
Yeah.
I know what that means. Yeah.
But also, one thing I was gonna say, we'll get back into it. I don't want to divert too much. Nerosky, one thing I really like about your approach is that you never do hand wavy stuff, and you never say proof is left for the reader.
Yeah, fuck that shit.
No. You take as many tangents as possible to make as little assumptions as possible, which is absolutely like, I feel like for me it is definitely something I appreciate a lot, because in most math textbooks they just be like, you should know this proof, and I'm just into another math book, and I'm like 7 textbooks later I'm still trying to figure out the original proof that I started from. It's nothing.
I see this done like in like answers to questions as well, but I've learned that in competition exams they usually take the harder solution and they post the harder solution, even if the teacher that proposed or the student that proposed the question proposed a solution that is way simpler and way more intuitive. They would rather choose their own more complicated solution to make the problem seem more intimidating and seem more like
the like ego, dude. Math marketing ego, bro. No.
Like I cannot state the amount of times I've done a problem by myself. I've had like a few, like maybe half a page written down. I go to look for the solution, and they shorten it. Right, they make some assumptions, they don't prove like every step, but the integral proof, like if you're gonna write what they wrote in like the solution, like the answer key on the exam, you'd get 0 points.
Oh,
right? It's that short, it's that shortcut. It's like it's meant for like people like at a high level to understand.
I think it's like
originally they are meant, they're meant for like teachers to understand, right? Like the people that grade your competition papers, they should understand that intuitively. But a student who wants to prepare for any competition needs like a step-by-step solution for everything, and you cannot find that anywhere.
Yeah.
Maybe it's a grand conspiracy to just keep like competition math tutors in business. You know, like the only way to get the step by step is to hire some dude for like $1,000 like an hour or something.
Yeah.
Or do what I did: take 7 courses in university that all use linear algebra.
Dude. Take out some college loans.
Yeah, this is why I've always wanted to like teach like people, like even for free. Like I enjoy this as much as I can.
Dope. Well, I'm glad we can provide a platform for you to do that.
Exactly.
Nice.
I'm more than happy to learn even more about linear algebra. At some point, I want to do some like all of the basic proofs of algebra.
I actually have a challenge now that I've shown you guys so many things about linear algebra. I've taught you like the basics already. Like I've taught you that induction is a big part. I've taught you what the characteristic polynomial is. You already know what eigenvalues is. So that's a big step forward. You know the Cayley-Hamilton theorem now, and I believe you have enough knowledge now to like try a competition, like even a local competition level, a question by yourselves, and I believe you'd manage it in like a few, like maybe.
We're gonna
10
be
minutes.
empowered. We're gonna be empowered. Yeah.
Yeah, like let's finish this off so it makes more sense for you guys, and I'm gonna give you one to challenge you.
Okay, cool. All right, so, all right, cool little fun side tangent. We came to this, and we said
learned a few things. Yeah.
We learned a few things, but okay. So then we get to Cayley-Hamilton, which is here, and we said, oh, the determinant of AB is 0. So applying that, we then get to.
We applied trace. Yeah, we applied trace to the Cayley-Hamilton theorem. Right. So since the determinant is 0, we are left with only like the first 2 terms.
I see. Let's apply trace.
Yeah, we apply trace. Yeah,
Gotcha.
the trace of the trace is just the trace. Yeah.
Trace is trace is trace is trace. Okay. And then the determinant of this was 0, so you're left with this minus this equal to 0. So if you then move that over, I guess you get the trace of AB squared is equal to the trace of AB squared. Right? Is that kind of what's happening here? Sorry, this is
careful. You cannot pull the square out of the trace. You can.
Right. Okay.
Pull,
so this is equal to the trace of AB plus BA, but then all of that squared. Is this kind of the key thing?
This is the key thing, but you cannot do this in general.
Oh.
This is something we've proven in this example. Yeah, if you look carefully, you do have this happening because you have the trace times itself.
Gotcha.
Yeah, and you already know that the trace of that is 0. Yeah.
Gotcha.
Not
right. Okay.
Square,
Okay. It's just because we have this special condition. This is not always true.
Yeah, this is not always true.
Okay.
You can pull constants out. You cannot pull powers out.
Interesting. Okay. Okay.
Yeah.
So.
Okay, so you're basically left with the fact that the trace.
But we said AB plus BA squared was 0. So don't I just get like 0 equals 0?
No. Yeah. No. Pause. From this. Okay. Sure. The trace of AB plus BA squared, like how do I differentiate them from one another?
I would say this is like
one.
the inner square. One. This is the outer square. It's called inner square, outer square.
Let's say the inner square. We already know the trace of the inner square is 0.
Okay. Why do we know it's equal to 0? Sorry. Oh, because AB plus BA squared is equal to 0? Wait, no. Sorry. That's just what we started with. Right. Okay. That was with this. Okay,
yeah,
we had that. Got you. Okay. This was given.
Yeah. That was the inspiration for Cayley-Hamilton.
Proven and inspode. Okay. Based or whatever we want to call it. Sure. All right. Awesome. So.
Right. So this means that the outer square is equal to 0. Which now you can take the square root of both sides and you reach that the trace is actually equal to 0.
And then, right, so if 0 is square root of trace AB plus BA squared.
Yeah.
Cancel. 0 is equal to trace AB plus BA. Okay, awesome.
Yeah. So can you look at the formula for Cayley-Hamilton again?
Yes. This was the whole formula.
The nicer looking one.
The nicer looking one.
Looking one, please.
Oh, this one right here?
Oh,
this one?
Yeah. Not my abomination.
Yours is not an abomination. Okay. This one. So this is 0.
The determinant and the trace is 0.
Yes, these are both 0. Oh, so C squared is equal to 0. Right?
So that's what I had written before. So AB plus BA all squared is equal to 0.
Okay, cool. Agreed. Oh, I see. Oh,
So,
you
what is AB plus B
sneaky
squared?
sneaky bastard. Because then you're gonna expand this out and be like, oh shit, this was by hypothesis, and this does have to equal 0, so this must be true. So this must equal 0, right? Because 0 plus 0 must equal 0.
Yeah.
Oh, and there you go, and then you get
Never
QED,
write
and then
that
you
on the
did
test.
it! Wow! Oh man, that's so cool. Right? Okay, I see. We just wanted to prove this was 0, so what we showed with our little trace, or Kaylee Hamilton little side quest, is we showed that this was 0, and then it was very easy to just show that. Okay. Man,
May I
that's
see the question, by the way?
yeah,
I wanted
for
to-
sure. Yeah, no, here's the original.
Okay.
It's in Romanian, but I think
Okay.
it says for matrices A and B that are dimension 2, show that.
of the complex spaces also very interesting.
Yeah. Okay. I don't know if that
Okay.
changes anything, but maybe.
Sometimes it changes
Oh.
because of the because of like sometimes when you have to change multiplication orders, it like I think it's like left. They call it the. Anyways, something with inner products. I forgot. Left symmetric and right
It,
anti-symmetric.
changes-
That's the one. That's the one. Yeah.
Wow, yeah.
Yeah.
That as well, but it does change eigenvalues a lot. So, but we
Eigenvalues,
don't use
okay.
eigenvalues here, so,
Yeah. Yeah. Okay. It
so
says
it doesn't
if
change anything. Yeah.
AB squared equals to negative 2AB, then prove that BA squared is negative BAB squared. Okay, yeah.
Yeah, if and only if. Yeah.
If and only if. Oh, okay.
Yeah.
Okay.
I don't know if you were here at the start, but I justified the fact that this if and only if becomes only a simple implication because the two statements are symmetric. So that means by replacing A with B and B with A, you get one another, right? So you only need to prove.
Oh, because like A and B are arbitrary, so like switching them over doesn't make
Yeah,
any difference.
it doesn't change anything. So you
Oh.
don't need like to go back and forth for each one.
Oh, that is cool. Okay, yes, that makes sense. Okay.
This also works for functional equations. So if you have like two functional equations, if and only if, like if they are symmetric, you don't need to prove. Like,
Oh, that's okay. Yeah,
the if and only if cases.
Okay, that makes sense. Yeah.
Best of luck, J
Also,
Gamer.
one thing
So
I was
that was yeah.
sorry. Go on.
No, you guys go on. What's up?
I was what the whole thing that with the trace of a matrix squared is equals to the trace of the matrix squared. That part, like, that means that if you assume like an n by n matrix, that means that the sum of the squares has to be equals to sum of all of the numbers squared, right? For the trace, for that identity to be true, correct?
Yeah.
Maybe.
So what would be the conditions on that matrix then?
I'm not
Isn't
sure.
there like a
Sure.
geometric average and like a something other average? Something
You want to
like
know how you prove this? Brampton, you prove this by Kaylee Hamilton.
that? Oh, not this one. No, just the condition for a matrix. For the trace
what
of
you
the
said,
matrix
yeah.
squared. Oh, okay. You use Kaylee Hamilton?
Yeah, I
for
know
that?
what you said. Yeah.
Oh,
So
okay.
what Kaylee Hamilton says, yeah. So if you have, let me write it out. So you have a squared minus the trace a times a plus the determinant of a times I2 is equal to 0.
Are you writing it somewhere? Sorry.
So then if the
I think he's gonna write it. I'll copy it in or something.
yeah,
Oh, okay.
I'm saying it. Yeah. So what you're saying is if the trace of a squared is equal to the trace of a all squared.
Yes.
Is that what you're saying?
Yeah.
Okay. So for a 2 by 2 matrix, the trace of a squared does have a formula.
Yeah, it would just
regarding
be a squared plus d squared.
No, it's gonna be the. Let me remember. It was something with the. It tied in determinants and the trace.
Oh, that's true, actually. Yeah, because it's not. Wait, the.
Yeah. Let me. Yeah, I believe I remember it. So it's gonna be trace of a squared is trace of a all squared minus 2 times the determinant of a.
Oh yes, you're right.
Yeah, I vaguely remember this for 2x2 matrix. I'm not sure for n by n. Like I'm not sure how you prove this for n by n, but I believe we can extrapolate it.
Oh, like induction maybe.
So yeah, maybe.
Yeah.
So like if you suppose trace of a squared is equal to trace of a all squared, those two cancel, and you get that the determinant is 0. No?
Yeah. So that would be the condition.
So then, oh right, so the determinant has to be 0 for a 2x2.
Yeah, in order for
I believe.
that.
Yeah.
Interesting. Okay.
Okay, nice.
The fact that I was teaching for 7 hours of math and physics and I'm still doing it.
Dude, it never ends, dude. Math is life, life is math.
Yeah, honestly, at this point, it's just
The way of being. Okay, very cool, Nerosky. I liked that. That was really fun. I also resonate a lot with what Rampton said in that, like, I learned a ton from all the side quest parts and really appreciated that there was no hand waving. And, like, you don't get this, you're dumb. That's the worst when that happens.
like, for example, one of the things that like there are sometimes simple things that they could be explained in much better ways, and it like it's not, and I feel like it should be. Like, for example, one of the common ones that I recently think, you know, the whole sine theta equals theta in physics assumption.
Oh, the small angle approximation?
Yeah, small angle approximation. This is the thing that pissed me off so goddamn much.
Why? What's wrong with it? Is it because sine of theta over theta is equal to 1 as theta approaches 0?
No, honestly, because here's the thing. What's because it doesn't
it's a
have
squeeze
to be
theorem.
much smaller than 1.
Isn't it a squeeze
No,
theorem?
it's like you could do it based on this, yeah, but there's a much better way to explain this.
Okay.
And it also makes sense as to what's considered small. This is just the first order approximation of the Taylor expansion of sine.
Oh.
And so say when you take sine theta, because it's supposed to be theta minus theta cubed over 3 factorial.
Yeah. Let me pull up the Taylor expansion. I remember. Yeah. It's this.
Yeah.
Whatever. Here. This looks. Yeah, it's the 1357, right?
Yes. So it's this one, right?
Yeah.
Nerosky, I don't know. Do you know about differential equations?
Yeah. I started studying them recently.
Okay, so let's say, for example, you're trying to do physics and you have the whole, like, a pendulum equation, right? You end up with a differential equation where the second derivative of x is equals to, like, sine x. This is for like a thing. And so in physics, they do this approximation where they say sine x or sine theta equals theta, small angle approximation that I hated for a very long time. It's just a first order Taylor series approximation. However, if you do decide to use the third order Taylor series approximation, then you can do this thing where it's called perturbation theory.
Okay.
So I think you probably would notice as well. And so what you would say is that because these we consider x as the main driver of this pendulum, and because x is smaller than 1, kind of, then x cubed would be smaller than x, so it would create extra perturbation in this main swing that it would have. And you would say that it's going to have some additional frequency to its angular frequency and some additional like time factor to the delay that it would causes, right? So you would say like t is equals to t plus epsilon t, t tau, and then you would do omega is equals to
something like this, right? I think they usually say like this, right?
It's t plus epsilon t, yeah, and then the omega becomes omega plus
the angular,
yeah,
it's like the resonant frequency, and then there's like the side bands, I guess, right?
And then you would solve it with this, and then you would get the pendulum equation with all the perturbation.
I see, because then this would go to t plus delta t, and then like, but you would expand out more terms here. Is what
it would be because that should be omega plus delta omega times t plus inside the bracket, right? You only have the t term.
Got you. Okay.
Yeah, but then the omega itself also has to be multiplied by it.
Okay.
Because it's sine of omega t.
Gotcha.
Normally.
Yeah. It's usually.
And then yeah, each and omega and the t gets multiplied by that. Yeah, like and this. Then replace the t's and the omegas with
t plus epsilon delta t.
Yeah, and then delta plus epsilon delta. And then you collect all the first order terms to give you the...
You get this. Like this?
Yeah.
I think?
Yeah. Plus t,
then,
minus...
Yeah, and then this is, whatever this is to the third.
Yeah.
Okay.
Yeah, exactly. And then, obviously, you can just logic your way into what would be the first order terms of omega and delta t. Or sorry, what would be the orders of the first order terms of omega and t? So like, yeah, the first you get the omega t, that's your basic.
Right. And then you have like omega delta t plus, what is it, like t delta omega plus, I guess,
and you collect all the first order
delta
terms.
omega delta t. Yeah, so I think you just carry
so delta
this,
omega
this,
delta
this.
t is 2 infinitesimals. This is
second order.
Those terms.
Yeah, that goes.
Yeah,
away.
exactly.
I see. So then, yeah, and then I guess some pop out here as well. Or wait, these are also like the third. Yeah. Okay.
And so this is like perturbation theory. That's the thing, is like I actually didn't get good at math until like I was in 4th year, but then I was backtracking all the math stuff that I learned. I was like,
that you just waved your hand over.
In real analysis, when I was getting destroyed, now I kind of get why, like, you know, different spaces, L2, L3, all these spaces, why they're important for quantum.
Yeah.
Because it's L infinity or something.
Nice. Super cool. Yeah, I remember this one. Nerosky, what do you want to do next? You want to give us like a baby one for us to try to solve ourselves? I don't know if I would.
I'm gonna give you a fun one.
Fun one? I love fun ones. What's the fun one gonna be?
Realizing how much we did already.
Yeah, look at all this. I mean, this is great. No, I mean, this is already a win in my book that we did all of this. This is like, oh my god, this is already
one
great.
Proof. Yeah.
It's just one proof with a bunch of, like, we had a side quest over here, we had a side quest over here, another side quest over here. Yeah, this was fun.
So,
it's the Baldur's Gate of math. Sorry.
The Baldur's Gate of math. Yeah. Which dungeon did we go down here? Which dungeon we go down here? Oh, okay.
You rarely see algebra and analysis combined into one.
Oh god, okay.
And this is one of those questions.
Okay. So, all right. Let A be equal to -3, 11, -1. I assume that's a 9. Is that a 9 or a 4?
4.
Dude, we got to talk about... Dude, me and you have the anti-symmetric 9s and 4s game, right? Because I do this and people are like, that's a 4.
Yeah.
You do this,
That's.
but this is a 9.
How do you write your 4s?
I write my 4s like this.
Okay, I do the other part first.
See, this to
You
me...
start with-
This
with
is a
your
9.
vertical line under 4.
But this is a 4. Okay, I'm gonna fix this. No, there you go.
Alright.
Okay, all right. Okay, fine. All right. -311, -14 is a matrix, a 2x2 in the real plane of things. Define a sub n for n is greater than or equal to 1. A sub n is equal to the trace of a to the n. A to the 0 is equal to the trace of I2. Find the limit as n approaches infinity of a to the n plus 1 over a to the n. Oh, wow. Okay.
So I'm gonna let you think of it.
Yeah, let me think about it. Well, let me think about what, like, for instance, I already see that they gave me big A. So I feel like I want to calculate. Well, I'm curious. Why did we give us numbers here when... And wait. Okay, so A0 is equal to the trace of I2. I2 is just 1, 0, 0, 1. And the trace of that would be equal to 2. I understand that. Okay.
Right. Yeah.
And then we say that
So,
A sub
what is
n...
A sub 1?
Okay, so a sub 1 would be equal to the trace of just a to the first power, which would be 1 as well. Well, just 1. Sorry, not 1 as well.
Right,
would
right.
be 1. Because I would just add these two together. Okay.
Sure.
So then, what would a sub 2 be? Well, that would be kind of messy, right? Because now I have to square. I got to multiply a with itself.
Surprise, motherfucker!
Oh man.
If you
I feel like-
want, I can
what?
pull out a calculator for you to help.
That's
you
okay.
Don't,
I think I
don't
can.
need to do this, but yeah.
You don't think I don't need to do this? But I kind of want to. What were you gonna say,
It helps,
Ranton?
it helps.
I have an instinct, and I wanted to ask if it's the right instinct or
Do
the
it.
wrong instinct.
There's no such thing as spoilers. What is it? What's the instinct?
Sure, but
Okay.
I'm not gonna tell you.
Oh,
Okay,
but he's
yeah.
not gonna tell
So
you.
Surprise,
Okay, my
motherfucker!
instinct always, whenever I see like trace of these as well, is like 1, try to get the a squared just to see what I get, and then if I don't get anything pretty, I'm just like diagonalization.
Like fuck this.
Just go straight into writing it as because the trace of a to the n is the trace of the p, like lambda to the n p.
Well, we had something. I think I might want to use the K. I might want to use the Kaylee whatever thing because there was something with traces in it there and things that were squared.
You are
Right?
You
Am I
are
the right-
getting closer.
I am getting closer.
I'm not gonna say anything.
Don't
You
say
are on the
anything
right
else.
path.
Don't say anything else, dude. Okay, I'm
I do think I do believe I missed telling you something, but I'm not sure if I'm gonna,
Maybe we-
gonna let you figure it out
Wait,
first.
1 second. I'm gonna also
We'll
do
figure it
this
out,
because I wanna also.
yeah. Let's learn.
I don't want to get spoilers. I'm gonna do something on my screen as well,
Okay.
and then I'm gonna see if I get something different. or-
You can also post it here in the chat later, and I'll just drag it in.
Okay, yeah, that would be.
What's up, Psychode? What's up, nerds?
That's dope!
All right. -3 times 11 is -33. -33 plus 44 is 11. So then I do this times this. Sorry, no, I do this times this to get this one. So that's going to be 3 minus 4, which is -1. And then I'm going to do this times this. So -11. -11 plus 16 is -5. No. -11 plus 16 is +5. Right? Okay, -11 plus 16 is +5. And the trace of that thing is just 3.
That is 3.
Okay. Here, I'll just say, like, trace of blah, blah, blah. Or trace of a squared. Is equal to 3. Okay. Where the trace of a1 was equal to
So-
1. Okay. And then this is equal to 3. Okay.
So now, since you did mention the Cayley Hamilton theory, the
I
theorem,
did, yeah.
Sorry.
Mm-hmm.
I can't add.
Why not apply it?
Yeah, let's try to do it. So, this is Kaylee Hamilton.
This is why this is why Kaylee Hamilton is powerful, because if you do have 2x2 matrices, you just slap it down and see what happens with your powers of A.
Okay, let's do it over here.
Right, so you're gonna get a lot of expressions for A squared. That's what's gonna happen.
I'm gonna get a lot of expressions for A squared. Okay, so this is gonna tell me.
I think I figured something out.
Okay.
This is very interesting.
A squared is equal to A. Trace of A. Well, the trace of A is just 1, right?
It is 1.
Or sorry. A squared minus A times 1 plus the determinant of A. Ooh, what's the determinant of A though? Determinant of A is equal to negative 12 plus 11, which is equal to negative 1.
Right.
Okay. So plus negative 1, so minus 1. Minus 1.
Yeah.
But then this
minus
is 1, 0, 0, 1.
I2.
Yep.
Oh.
And then this is all equal to 0.
No. Leave it as I2. Why are you doing that?
I just like this. I know this is
Matrix.
I2. Okay, fine. All right. I2 is equal to 0, 2. Cool.
Right, so move what you want to find stuff about A squared.
I want to find stuff
powers
about
of A.
trace of
So
A squared.
move everything else.
I can move everything over except for this.
Yes, so move everything else.
I think I want to say like
Yeah.
A squared is equal to A
It's intuitive.
plus this, and then I think
It is also intuitive because you have negative signs and you have a positive term. And
yeah.
you want
Anytime
to
I have
move the
negative
other
things
side.
here, I'm just like move the stuff over. I have some students I tutor who, for whatever, dude, it bugs me to like no end. If they have like x minus the square root of 4 like is equal to 3, they will literally always move the x over. They'll just be like, oh no, negative 4 minus is equal to 3 minus x, and then they'll move this over, and then it's like negative square root of 4 minus 3 is equal to negative x. I'm like, stop. Stop. Just move that over. Yes, okay. I moved the minus signs over. I think I want to take the trace of both sides, Nerosky. That seems to be a good strat, right? Or maybe not.
But you already know stuff about A squared, A, and I2. You're thinking right. You're thinking right, but for the wrong reason.
Okay. I know.
So you do want to take trace of both sides. So now you've already done everything that you have to do. You don't need theory anymore.
I don't need any
I'm
more of this
just
stuff.
gonna say that to you.
I feel like I wanted to find something. I feel
No,
like
you
I
don't need
wanted.
any more theory.
I wanted this shit. This shit looks cool. I want to go to this part of the dungeon
That does
and
look
like
cool,
take
but-
this out.
Yeah, you don't need that yet because
Oh, we
we
don't
don't know
need
that the rank of A is 1.
Exactly. Yeah. I don't know. Also, that the determinant's equal to 0. Yeah. Well, okay. Well, I know the determinant is definitely not equal to 0. We already did it. Yeah. Okay.
Yeah, we definitely will.
Okay. I'm gonna take trace both sides.
So what happens? So you want A to the power of n, right? That's what you
Eventually.
want. How do you get A to the power of n?
1 sec, and then this is just 1. Okay. How do I get A to the power of n? Yeah, because eventually, like big picture, let's like zoom out a little bit, right? I'm trying to find the limit of the trace of A to the n plus 1. Oh, sorry. The limit as n approaches infinity of the trace of A to the n plus 1 over the trace of A to the n, right? So I think it would be
And
nice.
You're gonna be very happy if you have A to the n plus 1 in terms of A to the n.
Correct. Yes. Okay. I see the inspiration here, right? Yeah. Okay. If this is related to this, then I can just take the as n goes to infinity. Okay.
Yeah. So how do you?
Well,
get that?
can I say that the trace of A squared is equal to the trace of? This is where I want to say like the trace of A to the n plus 1 is equal to the trace of A to the n, and then just plus 1.
No.
I can't say that. Okay. No. Never mind.
So I would, yeah, just delete the
All right.
taking the trace part
Oh, delete the taking the trace part. Okay.
because it's gonna be Yeah, because it's gonna trick you into doing stuff like that.
Yeah, it was getting me excited. I started hallucinating. I put on my tinfoil hat and I started trying to like find theorems that don't exist. Okay.
So how about you multiply this equation that you have? Is very nice. How about you try to get a to the power of n somehow from this?
Okay. Okay. So this is a squared, which is equal to a to the first. So can I multiply both sides by a to the n?
Yeah, sure.
All right, let's do it. So I'm going to say a squared multiplied by a to the n is equal to a to the first times a to the n plus the identity matrix, which is just a to the n. Yeah. Right, yeah.
Yeah.
Okay.
So you'd have a to the n plus 2 is equal to a to the n plus 1 plus
Oh,
a to the n.
interest. Are you allowed to do that? I always
Yeah, of
like.
course.
Okay, so this is the same as I can do exponent rules.
Yeah, you can.
Oh.
The same way you have the distributive property and the associative property.
We just don't have the commutative property. That's just the one thing. Is that the one property you don't get with matrices? Is this commutative? Everything else is fair game.
Yeah.
Okay. So I have a to the n plus 2
So-
is equal to a to the n plus 1 plus a to the n. But I
now,
want.
what happens if you take traces?
Oh, okay. Okay. Well, now let's take traces.
Yeah, because I was gonna say you had the right idea, but at the wrong time.
Yeah. Right person, wrong time, dude. Story of my life. Okay. Trace
Kinda like
of
that.
this is equal to the trace of this plus the trace of this.
Yeah, brilliant.
Love it. Now, is there anything cool about Kaylee, whatever the fuck that says something about that? No. Oh, we already took this from Kaylee. Okay.
Well, hold on. What is the trace of a to the n again? It's our sequence.
Trace A is our sequence? What do you mean, sorry, is our sequence?
Yeah, define the sequence a sub n.
Oh, duh.
Don't forget about it. Yeah.
Don't forget, dog. Oh, this is a to the n. Yeah. Oh, this is little a to the n. We should call it like b to the n. Okay. This is little a to the n. This is
Not
little
to the
a. Oh, sorry, it's just little
Sub n.
little sub n. Sorry. And then this is little a to the n plus 1, right? And then this is
Yeah.
equal to little a n plus 2.
Yep. And what does this look like?
This looks like a telescoping thingy. Don't forget the trace or the no, we don't need the trace because Psycode. Well, our original question here that we're trying to prove is that little a sub n is equal to the trace of big A to the n, and then that the limit of the n plus 1 trace over the regular n trace. We're just trying to figure out what it is. We're not trying to prove anything. Okay.
Okay, from this point on, this is all you.
Okay. I'm gonna divide everything by a to the n.
You should know how to do this.
Can I just divide everything by a to the n? Sorry, a sub n. Right.
A sub n.
Yeah. Let me divide everything by a sub n. I feel like that would help me out here. Okay. So then I have a n sub 2 over a sub n is equal to what I'm looking for.
All right, may I ask a question? I want to check the answer.
Oh,
Yeah,
Hang
so
on.
wait. We're almost
I
I'm
found-
gonna see if you got the right answer or not. Yeah.
I got the answer. Sorry, 1 second. Let me just double check. 1 plus square root of 5 over 2.
Yeah,
Okay. Is that the
That is-
correct answer?
that is the correct answer. Yes.
okay.
Okay.
Let's see. We got that.
I did it through what's it called? Eigenvalues.
Yeah,
do with
that
eigenvalues.
is the intended method. Yeah.
Okay.
Oh, that's the intended way
Yeah.
to do it.
Eigenvalues and the Cayley-Hamilton theorem are very closely related, so it's like either or in this case.
Okay.
I can post my solution.
Oh yeah, post yours. Yeah, let me see it.
Sure.
Let me check your work, dude. All right. So I'm trying to figure out what this is, Nerosky, and I know it's equal to this. So then I guess my question is, how does the trace of a to the n plus oh wait a minute is no is this true? The trace of a over the trace of b is equal to the trace of a over b? I don't think so, right?
No.
And,
Yeah, no.
All right. This is the thing I want to figure out. You say I have everything I already need, so let me think.
Yeah, I'll put that.
Let me see. Yeah, you do the characteristic polynomial. And you do prove something that I didn't tell Dr. Gold intentionally.
Oh.
Oh, the diagonalization proof?
The proof of the eigenvalues to the nth power. That proof.
Oh, that is my favorite proof. That was one.
Oh wait. You did tell me
I
that.
love that proof.
You
Because
told me
this
that
was-
here. Right? Is that this one?
That is very close to what Rampton
Or is it this one?
what Rampton did.
Which
The
one?
only reason that I know this proof is because this proof I memorized it, and it was 20% of my final exam in my linear algebra question. And
Yeah.
just because of that, because I knew this proof, I went up by a whole grade.
Wow.
I was like,
Yeah,
let's
this
go.
is a very powerful thing to know.
Okay, let me see what ran. Let me.
This
check
was
the-
one of my professor told me, if you're gonna know any proof from this like section, it needs to be this. And I was like,
Yeah, I intentionally left this out just in case you'd figure it out by yourself.
oh, okay.
Doing this proof.
Oh,
Okay.
that's very good.
Do you want me to set up the eigenvalue thing? I can set up the eigenvalue
No,
thing.
because this is also a solution. Like what you're doing right now is also a key to the solution.
Oh, it's another
Like
key.
this
Okay.
will-
I think where
this does work
I'm stuck
eventually.
here. How do I determine this?
So you divide it by a sub n,
Yes.
right? But you want two consecutive terms. You don't want a sub n plus 2 over a sub n, right?
Right. I wanted this one.
You wanted to divide by n plus 1 instead of n.
Oh, I
The
see.
motivation.
Oh, I also
Yeah, because
I also see what I did wrong here. This should have been this minus 1.
yeah, that sure.
Right? So then
Wait,
okay, sorry. So I had this, right? A sub n plus 2 is equal to a sub n plus 1 plus a sub n, right?
Sure.
I divided by a sub n, so that got
Yeah.
me here, right?
Sure.
So this goes to 1. This is what I'm looking for. This is just a
Yeah.
bastard. So then I moved the 1 over. So this should have been this minus 1.
Oh yeah.
Do you see what I'm saying? Sorry,
Yeah.
I made an algebra mistake. Okay. Now my
Yeah.
question is though, how do I relate two terms ahead?
So that's the thing. Let me give you a handout because I believe you're thinking like too theoretically for once.
Oh wow, thinking too theoretically.
What is the sequence that starts off as 0 and 1, right? So 0, 1.
Okay.
And the general formula is adding two consecutive numbers to get a third.
It's like Fibonacci.
That is Fibonacci. And now look at your occurrence relation.
Oh,
Like the
I
one
think
you divided by n
Oh, that's where the golden ratio comes from.
See?
So you're
AN
saying
plus
this
2
one?
is AN plus 1. Yeah. Not divided by A sub n.
Oh, just this one, right? Oh, it's a Fibonacci series. Oh, I see. The
Yeah.
next the two terms ahead is a sum of the two before it.
Yeah.
Sure.
So this is why you want to divide by A sub n plus 1 instead of A sub n.
Okay.
Right? Because you want stuff related to the furthest away term.
Okay. Okay, so one sec. This is +1, and then this is going to be is equal to 1 plus A sub n over A sub n plus 1?
Yep.
Right?
Yeah.
Okay.
Okay. Now, if the how do you call it? If the fraction had a limit, right? If our initial if our initial limit, like what we want to prove, like the limit as n goes to infinity of a n plus 1 over a n, had a limit, let's call it L, right?
Okay.
So limit as n goes to infinity of
Here, let's write it down here. Sorry. Let's say
yeah.
assume the limit limit as n approaches infinity of a sub n plus 1 over a sub n is equal to L. Okay.
Yeah, if it exists, yeah, and that is, yeah, sure.
Okay.
You are allowed to replace L in your recurrence relation. Have you done this before? Like when you have a recurrence relation, you know that the subsequences of a sequence tend to the same limit, if it exists.
Okay, so like the partitions of it have to go to the same thing, because you could just the partition just could be infinitely bigger, but like just missing one element.
Exactly.
Okay.
Nerosky, is that the Bolzano-Weierstrass?
No, that is something
Theorem?
else.
Oh, sorry.
No, that is,
What
the
is the
Bolzano,
name of the theorem that
this one that I just invoked?
Yeah.
I'm not sure. I think it is something related to Weierstrass, but it is not the Bolzano-Weierstrass theorem. That is relating to the fact that a function, if it changes sign, it has a solution on that interval. That is the Bolzano-Weierstrass theorem. I'm not sure if it is for sequences.
Okay.
Though. Yeah, but this is definitely not that.
Oh, okay. Yeah.
This is provable by neighborhoods, and it's pretty difficult of a proof to conceptualize. But you can replace like the fraction you have, an plus 1 over an equals L, back into your recurrence relation, if you take the limit on both sides.
Okay, let's take the limit on both sides.
Okay.
All right, so I'm gonna take this. I'm gonna take the limit as n approaches infinity, right?
Yeah.
Let's do the limit as n approaches infinity. This one. Okay.
Yeah.
This is 1
So,
over L
hey-
then. No, right?
Yeah, it is 1 over L. Yeah, nice catch. And that is L on the left-hand side.
Ah, okay. Because I can just say that n equals n minus 1, whatever, u equals n minus 1 or whatever. I can just
Sure,
reindex
yeah.
this. And then,
This is what I was saying. Like by
Okay,
the
this is basically L.
yeah.
And then this is 1 plus 1 over L.
Yep.
Oh,
So multiplied by L, move to the one
oh my
side.
god. L squared equals L plus 1. L squared minus L minus 1 equals 0. Oh, I guess you gotta do the quadratic formula, right? X equals -1 plus or minus
Yeah.
the square root of 1 plus 4 all over 2. So you get -1 plus or minus the square root of 5 over 2.
Nope. How? You did everything right but the sign of -1. It
Oh,
is
did I
negative,
did I go
negative
wrong?
1.
Okay, sorry, my bad.
Negative, negative 1.
There we go. Okay, now I got it. It's a positive 1.
Very nice. Yeah. One more thing.
One more thing. All right, what's one more thing?
You have two values for the limit. You have the 1 plus square root of 5 over 2 and the 1 minus square root of 5 over 2.
Mm-hmm.
Now, what happens if it is the negative?
The limit's negative, then.
Can that
Right.
happen?
Can you have a negative trace?
You can have a negative trace, but
Oh,
can it
but
happen in this case?
I don't think so, right? Because how could this over this get you a negative? One of them would have to be negative, other one would have to be positive. That wouldn't make any sense,
Yes, exactly.
right?
And it's also an increasing sequence.
Oh, I see. Yes, because it's squaring. Well, okay. What's the difference?
Yeah.
Oh, no. Yes. We know it's increasing because what? I looked at the first two terms and said yeah, or I guess it would be.
You can also.
How could you tell that the
also
matrix
show,
is increasing with the trace?
First off, if the trace starts off as positive, raising the matrix to any power will not make the trace negative.
Oh, okay. I didn't know that.
Intuitively, like if you have a positive number, squaring it is not gonna make it negative.
True.
Or cubing
I
it,
just
anyway.
wondered if like the inner elements, like the negative ones, could somehow get bigger than the positive ones, and then the trace could flip negative.
Yeah, no, that couldn't happen. No, it could.
I see.
Like it could happen that it gets close to 0. It doesn't, but it could happen. But in any case, it never is negative. So
Hamiltonian says you can also check the first two terms of the sequence, which we did, right? We showed the trace of a to the first is 1, the trace of a squared is 3. Is it because it has to be monotonic? It's either increasing or it's decreasing?
yeah, it is. You can prove it rigorously, but you don't need to because it's just raising it to the power,
Oh,
right?
okay.
So it's just trace of a matrix to a power. That is never negative if it starts off as positive.
I see. Got you. Wow, that's super rad.
I had a question, Nerosky. Is the name of the theorem Heine-Borel? Is that the one?
Fine. That is.
Because it talks about the compact, every bounded on closed set is compact, and every cover of S has a finite subcover.
So I know. So Heine-Borel.
Yes. I don't know if I'm understanding the theorem correctly.
The one that says like subset S of a Euclidean space R to the n. Is this one? If a set is compact, then it must
yes.
be closed. I'm not sure.
Yeah.
No, I'm not
Okay.
sure.
Okay.
I could try and find
sorry.
it for you.
Okay, no, that's okay. Yeah, sorry, I don't want to distract you
okay.
too much. I was just curious because I remember about that theorem, but I forgot its name, so it was just kind of in my head.
There is
Nice.
another theorem. There is another theorem for Heine that Heine has. It is about functions. I'm not sure if you know it, but it is. It's pretty intuitive. It says that if f is a function and a is an accumulation point on its domain, if the limit as x goes to that accumulation point of the function is equal to L, and it is a real number, then any sequence that converges to that accumulation point
Will also have the same limit?
will also have the same limit, exactly.
Okay, yeah. That makes
Yeah,
sense.
that is another theorem of Heine. Yeah.
Okay.
This one had
Yeah,
slightly
and
less
this
dungeons.
also, yeah. This one is very straightforward. That's why I gave it. It's
I don't
actually
know
from the.
I don't know if it was
It's
straightforward.
the second. It's the second problem from the 2016 local phase of the Olympiad in Romania.
Ah, okay. So this is like the qualifier for like the high school kids or something?
Yeah, this is the qualifier for the big boy leagues.
The big boy leagues. We're gonna get there
This-
someday, chat. We're gonna get to the big boy.
When I get to studying for the county Olympiads, I'm gonna come with some big things.
I can't wait. I can't wait for us to start lifting really heavy weights and getting really strong in math.
Yeah, I'm gonna be coming around with sub-algebra.
Y'all are gonna fucking learn.
Oh my god. Here's the thing. If you can ever teach me measure theory, I will 100% be down for someone to teach me measure theory.
Measure theory.
I'm gonna have to teach myself measure theory, but then yeah, sure.
Once Nerosky acquires the
if you
knowledge.
ever want to teach it, I would just say if you ever learn it. I mean, I always tried. I've attempted multiple times, and it's so dry. Sorry.
It is, yeah. It's very difficult.
So hard. It's so hard to get it to measure theory. There's no visualization. I'm a visual person, so I love geometry. So differential geometry was very fun for me. But measure theory, I was just fighting every urge not to throw the book out the
End
window.
yourself.
You're not that guy, pal. Trust me. You're not that guy.
I've attempted so many times to study. But yeah.
Sweet. I need to start the chess tournament in like 2 minutes. So,
Oh, I forgot about that.
yeah, we're gonna do the. What's up, Tuma? Tuma, you wanna come and say hi? Well, wait, one sec, Tuma. Let me. When we go to recess, we're gonna go to recess in like 2 minutes. Tuma, come join me there, and then you can hop on, whatever. This is awesome. Nerosky, I wanted you to maybe like say any like closing words you want, and then like I'm gonna super, shout you out and talk about things, and then we'll go play chess.
Sure. Yeah, I'm gonna be joining for the chess tournament as well.
Oh fuck yeah! I'm gonna get beaten the shit out of, but
Chess tournament?
we're gonna do a chess tournament after this. Yes. In like 2 or 3 minutes.
I was gonna hop out, but I wanted to stay around for a little bit, or I might keep the Twitch.
Yeah. So we'll go raid our sister channel, Actual Gaming, and that will be streaming the chess tournament, which starts in a couple minutes.
Okay.
So
Also, Nerosky, thank you for teaching as well. I mean,
yeah,
Good job.
I learned a lot, definitely.
I love it. It's great. Nerosky, what do you want to say?
How do I join the chess club?
Oh, it's in the announcements. If you go to announcements, Friday chess tournament. Here, I'll tag you. There's a link to join the chess club on chess.com, and then you click on the tournament and you can register for it.
I sent a request to join.
Oh, okay, cool. Let me add you in then real quick. Pending requests. Got it. All right, Physion, is that you, Physion?
Yeah.
Cool. All right, you're added. Okay. Cool. All right. Nice. Okay, so let's give Nerosky a big thank you. Round of applause, claps, all that stuff. I super appreciate this stream. I think it's been fucking dope.
That's dope.
I've learned so much, Nerosky. I love all the little side tangents. I will resonate with everything Ramton said about you're an amazing teacher at like not hand waving and being very patient with my level of dumbness sometimes trying to like understand concepts. But I feel better at the end of it. I hope everyone else who watched also feels the same way.
Yeah, and like I believe like in a few moments, like in a few of these sessions, like maybe in a month or two, I believe all of these like lapses in what you call now like stupid moments, I believe you're gonna look back and see like, how did I not know this?
It gets so strong. I love it, dude. I think learning is eternal, lifelong, never ends, and so this is another beautiful example of how we should always just be leveling up in life constantly, and this is one way to do it. And we're fortunate to have awesome people in our community like Nerosky who are willing to teach awesome things like this. So yeah, I appreciate you, dude.
Good job.
Fucking dope.
Let's go.
Thank you, Dr. Gold, also for letting me always, crash your stream. And
you're never a crasher, dude. You're never a crasher. and also,
I'm trying to get in on it as well. Like I'm preparing some context, some stuff that just slowly gonna maybe like do some stuff online as well.
Well, we're gonna see you tomorrow. So make sure come on by tomorrow at 1:00 Pacific. We're gonna be doing the Golden Hour podcast with Ramton, and Ramton's and I are gonna discuss like the foundations of proofs. So another really cool intellectual. Same thing. I'm gonna come in like kind of knowing a little bit, just like maybe some of you guys know in the audience, and Ramton's gonna show us the way. Be a wizard.
Well,
Love it.
thank you.
Yeah. Okay. That being said, let's go raid. Dude, how do I raid my own channel, dude? What? Where is my own channel? There we go. Okay, I'm gonna go raid the chess channel. So if you wanna just stay in this Twitch, it's gonna take you over to our other channel, Actual Gaming. I need like 5 minutes to restart this PC because it's like choking right now for some reason. I don't know. But the stream will still be up, and then make sure you register for the chess tournament if you haven't, because it's gonna start in 13 minutes, and I can't add people after that. So you have to be registered. You have to be signed up for it. We are going to stay live during chess. I'm going to move us all over to recess, though. We're going to exit office hours. Okay. Cool. All right. Thank you again, Nerosky. This was fucking dope. We will see you guys tomorrow at 1 o'clock for the Golden Hour AMA podcast. And then if you want to come play chess with us, we'll be over on Actual Gaming starting now. Peace.